Last week we were talking about putting functions together, compositions of functions, addition and subtraction, multiplication. And whenever you see a function that has an x on the outside, what they're really asking for is they're asking you to find an equation. If there's a number here, they're asking for a value. If there's an x on the outside, they're just asking you to add these two equations together, f plus g. So my f of x function is x plus 3. My g of x function is x minus 3, so I just have to add those together. And if you add those together, you just end up with 2x. In this problem, it's just a multiplication. It's just f times g of x, and since it's an x here, they just want me to find the two functions multiplied together, so I'm just going to multiply 1 over x squared times 1 over x to the 4th, which ends up being 1 over x to the 6th power. In this problem, it's a subtraction problem, but it has a number here. So what they're really asking me to do is they're asking me to find f of negative 3. So I could rewrite this as f of negative 3 minus g of negative 3. That would give me the same answer, or I could combine the two functions together and then plug in negative 3. I like doing it separately. So I'm putting negative 3 in here. Negative 3 squared is 9 plus 5, so that gives me 14 here. Minus, I put negative 3 in here. Negative 3 minus 6 is negative 9. So I have 14 minus negative 9, which just turns out to be 14 plus 9, which is 23. In this problem, now there's a little O here, which means it's a composition of functions. We're doing a composition. So if they want me to find f of g of x, or they really should be an x here, this really just, I usually write it this way. So I'm just going to rewrite this as f, and then g of x is x minus 5. Now this is telling me to plug x minus 5 into the f function. Well, the f function is x squared, so I just do x minus 5 quantity squared. This week we're going to be talking about inverse functions. A fairly easy thing to do to work with inverse functions. We know that a set of ordered pairs can represent a function. For instance, the function f of x equals x plus 4 can be written out as a set of, if I put in 1 in here, I get 5. So if I put 2 in here, I get 6. So it's really a t-table, if you think about it, putting in 1, 2, 3, and 4, and my y values are 5, 6, 7, and 8. Okay, so that is a function. We could write them out as ordered pairs. In this case, by interchanging the first and the second coordinates of each of these ordered pairs, you can form the inverse function. So an inverse function, when, let me go to a clean sheet. Okay, so let's say I gave you f of x equals x plus 4. And we said that the function, we made out the t-chart, and we had 0, 1, 2, and 3. So if you put 0 in there, you get 4. You put 1 in there, you get 5. You put 2 in there, you get 6. You put 3 in there, you get 7. Okay, so my ordered pairs are 0, 4, 1, 5, 2, 6, and 3, 7. Okay, so now if I write the inverse function here, and algebraically to write an inverse function, instead of writing f of x, I just rewrite it as y is equal to x plus 4. And then the steps algebraically to write an inverse function is you just flip-flop the x and y around. So this would be x equals y plus 4. And then you solve for y. So if I subtract this, I end up with y is equal to x minus 4. This is my inverse function. And it's usually written out this way, f, and we put a negative 1 here. So that represents inverse function, and that's x minus 4. Now, let's take a closer look at a very interesting observation now. So now, let's say these are my x values, 4, 5, 6, and 7. 4, 5, 6, and 7. So if I put 4 in here, 4 minus 4 is 0. If I put 5 in here, 5 minus 4 is 1. If I put 6 in here, 6 minus 4 is 2. If I put 7 in here, 7 minus 4 is 3. Look at that. An inverse function, look at what it does to the ordered pairs. So an inverse function, if you plug x in, you get, or for the original function, you put x, you get a y value. But for the inverse function, it does exactly opposite. It takes the y value and it gives you the x value back out. That is what an inverse function does. Okay? Now, if we graph, now let's take a look at another interesting concept with inverse functions. Let's graph out our regular function, x plus 4. So I go 1, 2, 3, 4. It's my y-intercept, and my slope is 1, so it looks something like this. Now, if I graph out my inverse function, x minus 4. So I go down 1, 2, 3, 4. Now, this one, it's not so obvious what an inverse function does, but I will tell you that if you draw the line y is equal to x, that is this line right here, inverse functions are always mirror images of themselves along the axis y is equal to x. So if I folded, if this was on a piece of paper and I folded it on the green line, the blue and the red will end up on themselves because inverse functions are reflective about the line y is equal to x. So there's a lot of interesting phenomenon that goes with inverse functions. First thing is the ordered pairs. If they give me ordered pairs and they said, what is the inverse function? Well, all you have to do is just flip those ordered pairs around. That's how easy it is. Okay? If I wanted to write an inverse function, all I do is I rewrite the function. If it's y is equal to x plus 4, you just flip-flop the x and the y around. Now, you can have much harder problems. I mean, there's no saying that it's an easy problem like this. So let's say I gave you a problem like y is equal to, let's go, 3x plus 4. I mean, I know this isn't real difficult, but let's do the same thing with the ordered pairs here. Okay, so if I put 0 in there, 0 times 3 is 0, plus that gives me 4. If I put, oops, sorry about that. Let's go 0, 1, 2, 3. So if I put 0 in there, I got 4. If I put 1 in there, I get 7. If I put 2 in there, I get 10. If I put 3 in there, I get 13. Okay, so those are, so my ordered pairs would be 0, 4, 1, 7, 2, 10, and 13. So now if I wanted to know what the inverse function is, so let's do it in a different color. I will tell you that my inverse function is going to be 4, 0, 7, 1, 10, 2, 13, 3. It just flips these around. So it would be 4, 0, 7, 1, 10, 2, and 13, 3. So now let's write the inverse function here. Remember what I said. You just flip the x and y around. So I go x equals 3y plus 4. Solve for y. That will be your inverse function. So I'm going to subtract 4 off of both sides. That gives me x minus 4 is equal to 3y. Divide through by 3 now. So I end up with y is equal to, what is that, 1/3 x minus 4/3. Whew. So that's my inverse function, and I usually write it this way. All right, so let's take a value. Let's take 4. Let's put 4 in here. So if I put 4 in there, 1/3 times 4, that gives me 4/3 minus 4/3 is 0. Holy cow, it works. If I put 7 in here, that would be 7/3 minus 4/3 is equal to 3/3, which is 1. Oh my goodness, it works. So now let's try graphing these two functions. Okay, so 3x plus 4, do that in green. Okay, so I go up 1, oops, it's not my pencil tool. So 1, 2, 3, 4, and then 3/4, like that. Now my inverse function is going to be really hard to graph because I got 1/3 x minus 4/3. Okay, -4. So that goes. Let's change colors now. Do black. So that's about 1 1/3 negative, and then my slope is 1/3. So I go up 1/3. So that's going to look something like this. Okay, now what did I say? I said it had to be, if you drew the line y is equal to x in there, so let's do that in a different color. If I drew this line y is equal to x, if I folded it along that line, it should be a mirror image of it. And it is. So that really talks about all of the inverse function stuff that we're going to be dealing with today. But let's go through the slide still here. All right. Let me go back to my slides. talked about that. We're down here. Okay. Find the inverse of f of x equals 4x. Now, I'm not 100% sure we're supposed to be dealing with the algebraic way of doing it, but if we were, if I was doing this algebraically, I would rewrite this as y is equal to 4x, then x equals 4y, divide through, so my inverse function is going to be x over 4. And we can check ourselves really easily. And the way I always check myself on these types of problems is I just take a couple values, and I'll put a couple values in my original function. So 0 times 4 is 0, that gives me 4. If I put 2 in there, that gives me 8. Then I go backwards. So I put 4 in here. 4 over 4 is 1. If I put 8 in here, 8 over 4 is 2. So it does, the inverse function does give me what I originally started with. So that's how I always check my inverse functions. Okay. So now they're just talking about the -1. When you write it this way, this f to the -1 power just represents that it's an inverse function, that's what you're dealing with. The graph of an inverse function. The graphs of a function f and its inverse are related to each other in the following way. If the point AB lies on the graph of f, then the point BA lies on the inverse. We talked about that. This means that the graph of f inverse is a reflection of the graph of f along the line y is equal to x, and that's this line right here. Okay? It says sketch the graph of the inverse functions f of x equals 2x minus 3 and its inverse 1/2 x plus 3 on the same rectangular coordinates. We can do that. 2x minus 3 goes down here, then slope is 2. So it looks something like this. Then my inverse function, I'm just going to rewrite that as 1/2 x plus 3/2. I use a different color when I graph it. So 3/2 is like 1.5. And then my slope is 1/2. So up 1 over 2, up 1 over 2, up 1 over 2. That is my graph. And now if I draw on the line y is equal to x, different color here. That's the line that splits the graph directly in half. You can see if I fold it along there, I should have an inverse, or it should be a reflection along that line. And here are the points. Here are some points for the equation 2x minus 3. And then if you take a look at the inverse function, they're just opposites. A one-to-one function. What is a one-to-one function? The reflective property of graphs of inverse functions gives you a nice geometric test for determining whether a function has an inverse function. This test is called the horizontal line test for inverse functions. And this is what it says. A function f has an inverse function if and only if no horizontal line intersects the graph of f at more than one point. Here is an example. If I had a graph of y is equal to x squared, okay, this is y is equal to x squared. If I drew a horizontal line in here, it touches the graph in more than one spot. That means that this does not have an inverse function. Okay? Now some people would say, well, I could write an inverse function for that. Well, sure, you could write one, but it doesn't have an inverse. That is going to be a function. Okay? And the reason is, remember, to be a function, vertical line test has to work. So if I think about this one, if I rewrite this, so x equals y squared, and rewrite this so y is equal to the square root of x, yeah, well, the square root of x looks like this, doesn't it? Now, if somebody would say, well, but Ms. Schenken, you have to do plus or minus, okay, then you'd have this one. Well, guess what? This is not a function, because the vertical line test tells us that if you draw a vertical line and it touches in two places, this is not a function. And that's what this whole thing goes about. It says a function f has an inverse function if and only if no horizontal line test intersects the graph. Well, that's because if you rotated this down, this is no longer a function anymore. It's a relation, but it's not a function. So the horizontal line test tells us if when we take the inverse function, if that is going to be a function. Okay? A one-to-one function of a function f is one-to-one when each value of the dependent variable corresponds to exactly one value of the independent variable. A function f has an inverse function if and only if it is a one-to-one. So if you have a function and inverse is a function, then we say it is a one-to-one function. Okay, so here's an example. The graph of x to the third minus 1 is shown. Here it is. Because no horizontal line intersects this, this is the original thing is a function, and that means the inverse is also going to be a function. Therefore, x to the third minus 1 is a one-to-one function. Here, I have x squared minus 1. The original function, the original graph is a function. Okay, we know it's a function because a vertical line test tells us that it is a function. However, since the horizontal line, since when I draw a horizontal line in there, it touches in two places. Okay, it touches here and here. That means that its inverse function is not going to be a function. Therefore, x squared minus 1 is not a one-to-one function. And the reason it's not a one-to-one function is because the inverse function is not a function. And we did a graph of that before, and we saw that it was not a function. All right, finding inverse functions algebraically. And we talked about this already, about finding an inverse function algebraically. So that's one of those things that, you know, it's a relatively simple thing to do. All you're going to do is you're going to interchange the x and y, and you're going to solve for y. Okay, so here are some examples. Oops, that's not my examples. All right, so if I wanted to find an inverse function, so let's do this problem all the different ways and talk about if it's a function, if it's not a function, if it's inverse, if it's a one-to-one function. Okay, so the first thing I do on these types of problems is I'm just gonna make a table out here, x and y, and let's just put a couple of values in there. So 0, 1, 2, and 3. And if I put 0 in here, 3 times 0 plus 4, that's going to give me 4. If I put 1 in here, it's going to give me 7. If I put 2 in here, it's going to give me 10. If I put 3 in here, it's going to give me 13. So this is my regular function, f of x. Okay, so now, if I wanted to find some values of the inverse function, remember, we already talked about this, it's just the opposite. So if 0, 4 is on the regular function, I know that 4, 0 is on the inverse. If 1, 7 is on the original function, then 7, 1 is in the inverse. Same thing here, 10, 2, 13, 3. Okay, so the inverse function just flips the x and y around. Now, if I was going to graph this, my graph of y is equal to 3x plus 4. So I'm going to go up to 4, 1, 2, 3, 4. And then my slope is 3, so that's up 3 over 1. So that's going to be this graph right here. Now, I don't know what the inverse graph looks like just of yet, so let's find the inverse function. Okay, so the inverse, well, let's talk about, is this a function? Remember, a vertical line, if I drew any vertical line, it only touches this in one place, so this is a function. So, is a function. Sorry about that. I'll turn this off. Okay, so this is a function. All right, so now I'm going to find the inverse. So remember, to find the inverse, we flip-flop x and y around. So x is equal to 3y plus 4, and then we solve for y. I'm going to subtract off 4, so x minus 4 is equal to 3y. And then I'm going to divide through by 3. So x over 3 minus 4/3 is equal to y. So this is my inverse function, and I write it this way. The inverse of x is equal to 1/3 x minus 4/3. Okay, so if I'm going to graph that, so let's graph this one. So negative 4/3 is down here someplace. And then 1/3, so I go up 1 over 3, up 1 over 3. Oh, that should be farther over. Up 1 over 3. I'm just estimating this. All right. So now, is the inverse function a function? Yes, it is. How did I know that? Well, if you drew a vertical line, it's a function. So remember, if the original function and the inverse function are both functions, this is a one-to-one function. So it's just a bunch of terminology this week. So this is a one-to-one function. All right, and in order to tell that this is an inverse function, the last thing I do is I always draw the line y is equal to x in there. And if it's reflective, if you folded it on this blue line, the red line and the green line should go on top of each other. That is my last thing to check to see if it is an inverse function. So, we did. We found that this was a function. Its inverse was a function. That means it is a one-to-one function. We also talked about the ordered pairs. If 0, 4 is on the original function, then I know 4, 0. Now, we could check that. Guess what? If I put 4 in here, 1/3 times 4 is 4/3, minus 4/3 is 0. We knew that. We knew that if you plugged in 4, we're going to get 0 out. If we plugged in 7, we should get 1 out. So if I plug in 7 here, 1/3 times 7, that's 7/3, minus 4/3 is equal to 3/3, which is 1. Yay, it works, okay? So inverse functions are fairly easy to do. Algebraically, trying to find them, really easy to do. So not a lot of hard stuff this week. All right, let's take a look at another one. It says find the inverse function, or find the inverse of the function. Okay. Now I would rewrite this as y is equal to 3/2 x plus 4 over 2, or just 2. It's much easier than having it written out like this, because that 2 goes to both terms. So now if I'm going to rewrite it as an inverse, I just flip-flop the x and y, and then solve for y. So I'm going to subtract off 2, so that's x minus 2 is equal to 3/2 y. And then I'm going to multiply through by 2/3. So 2/3 x minus 2 is equal to y. If I multiply through here, I end up with 2/3 x minus 4/3 is equal to y, or f inverse of x equals 2/3 x minus 4/3. Now, to check myself, I just will take a value. So let's plug a value into f of x. So let's just put 2 in here. So if I put 2 in here, 3 times 2 is 6. 6 plus 4 is 10. 10 divided by 2 is 5. So that is a point on the original function. So that means if I did this correctly, if I plug in 5, I should get 2 out. Okay, so if I plug in 5 here, 2/3 times 5, okay, that's 10/3. 10/3 minus 4/3 is 6/3, which is 2. It does work. This is the inverse function of that. So you can always check yourself real easily to see if you did the problem right. Just take a value and plug it in. The x and y just flip-flop around. All right. Find the inverse of this function. All right, again, I'm just going to rewrite this as y is equal to, and then I'm just going to put the 2. So this is going to be 5/2 minus 3/2 x. Okay? Flip-flop the x and y. So x equals 5/2 minus 3/2 y. I want to solve for y now, because that will be my inverse function. So I'm going to add 5. I'm going to subtract 5/2 off. So I've got x minus 5/2 is equal to negative 3/2 y. Now, in order to get rid of this, I'm going to multiply both sides by negative 2/3. So I end up with negative 2/3 x plus, what's that going to be, 5/3, I think. That is my inverse function. Now, again, I'm going to check myself, because I could make mistakes easily. So the first thing I do is I just ask myself, okay, I'm just going to plug a number in here, just in my original function I want something that comes out halfway nice. So let's put 5 in there. So if I put 5 in for x, 5 minus 15, that's negative 10 over 2, which is negative 5. So if I plug in 5, I get negative 5. Now, for my inverse function, if I put negative 5 in, I should get positive 5. So if I put negative 5 in here, that gives me 10 thirds plus 5 thirds, which is 15 thirds, which is 5. Oh, it works. This is the inverse function. All right. This should say practice 13. All right. It says use the property of inverse functions to find the inverse of f of x equals x plus 3. Well, that's a pretty easy one. So I got y is equal to x plus 3. Flip-flop the x and y, so I got x equals y plus 3. Solve for y, so x minus 3 is equal to y. We'll just rewrite it as f inverse x minus 3. Oh, that one's a little bit tougher. It says find the inverse. Well, it doesn't matter how it looks. We do the same thing. So I flip-flop the x and y, so this gives me x equals 1 over y plus 3. Oh boy, all right, well, I'm solving for y, right? So I'm looking at this thing and I'm thinking, okay, how am I going to solve for y here? Well, I know this little trick that, you know, if you have something like 2 over 1 is equal to 4 over 2, that's a true statement, right? 2 over 1 is equal to 4 over 2. If you flip these over, 1/2 is equal to 2/4. If you have a fraction on one side and a fraction on the other side, you can flip them over. They're still equal. So I'm going to do that. I'm going to just rewrite this as 1 over x equals y plus 3 over 1. Well, I'm solving for y, right? So I'm just going to subtract off 3. So 1 over x minus 3 is equal to y. That is my inverse function. My inverse function is 1 over x minus 3. So I'm going to go with letter C here. Find the inverse of this function. Oh my, x to the 11th power plus 3. Okay, it doesn't change the way I solve this thing. I mean, we still do the same thing. We flip-flop the x and y around. So x equals y to the 11th plus 3. I'm solving for y, so I'm going to subtract off 3. So x minus 3 is equal to y to the 11th. Well, the only way to get rid of an 11th power is to take the 11th root of both sides. So I've got the 11th root of x minus 3 is equal to y. So my inverse function should be the 11th root of x minus 3. Let's see here. When in doubt, choose C. Looks like C is the answer again. Whew. All right.